In this video, we're going to talk about projectile motion. Nice. Hello everyone. So in this video, we're going to talk about projectile motion, which is just a certain kind of 2D kinematics. So let's review some of the kinematics that we've discussed already in multiple dimensions. And we'll do some things with switching reference frames, and then we'll get to some projectile motion example problems. Okay, so just a bit about coordinate systems to start out. So we're going to use a 3D coordinate system with unit vectors I hat, j hat, and k hat, and I also use x hat, y hat, and z hat. They're just the unit vectors that are pointing along the x, y, and z axis, right? So these figures show, right on the left here, we see the coordinate system that we'll be using, right? So I, j, and k just point along x, y, and z. And so for any point P, you can describe that point by a position vector r, which will have as its individual components the x, y, and z location of that point. So the individual unit vectors have length unity, right, length 1. If I have a coordinate position, x, y, z, then I can just multiply each of the individual unit vectors by that magnitude there, x, y, and z. And when I finish up, I'll have a position vector r that's equal to x times the x unit vector, y times the y unit vector, and z times the z unit vector. So this will give me a single vector that has the position of my object. And if those coordinates are changing with time, then the position vector will also be a function of time. So equation 1 then is my position as a function of time, and then equation 2 and 3 give the first and second derivative of that position vector. Those are the velocity and acceleration vectors. And it's noteworthy here that the individual components here, the x, y, and z component of each one of these three equations are related through derivatives, but the x component of one property is never related to the y component of another property, or the z component. The individual components behave independently of one another. So for example, if there's some acceleration happening in the y component, that was not going to change any of the kinematic properties in the x component. Okay, a bit about displacement. So we've talked about displacement in 1D setting, now in a 2D context. So if you have an object that's moving and between two time points, say t1 and t2, and it moves here from point p1 at t1 to point p2 at t2, with the vector locations given by r1, this vector here, and r2, this vector here, then the displacement vector over that time span from t1 to t2 is going to be just the difference between the two position vectors here. So r2, the final location, minus r1. And the displacement vector is, note that it points here from p1 to p2, and it doesn't care about the path that was taken between p1 and p2. It points from the starting position to the ending position, and that is completely independent of, say, what's shown here as delta L, right? The total arc length, the total distance that's traveled over there. The displacement is just a vector that points from starting location to final location, has the effect of the path between those two is nothing on the displacement vector. Okay, so we'll get to example problems very quickly now. So just a little bit about reference frames in 2 dimensions. So let's just say that you have 2 reference frames, one called R1 and one R2. And you can just think of reference frames, right? Like they're points of view, essentially. They're things that you can attach coordinate systems to. So I've used the example of a train, and you could think of R1 being the reference frame of somebody sitting on a train, and R2 being the reference frame of somebody outside on a park bench who's sitting outside of the train and can see in through the window, and they will see the same phenomena, but they will describe it much differently. The kinematic properties will appear different to them because of the reference frame that they're in. So if we have R1 moving with velocity, with this velocity here, moving with this velocity here, according to the reference frame of R2, or according to the observer who's sitting there in R2, then R2 will appear to move with velocity, with the opposite velocity from the standpoint of R1. So the person on the park bench sees the train move at 100 meters per second to the north, and then the passenger on the train sees the park bench moving at negative 100 meters per second, right? So it's moving to the south. If an object travels with velocity, with this velocity, the object in R1, and that's from the standpoint of an observer, say, sitting on the train in R1, then an observer in R2 will see the velocity of the object to be that velocity that the object had in reference frame R1 plus the relative velocity between the two reference frames there. So essentially what that means is if you see somebody, if the person on the park bench sees somebody moving at 10 meters per second towards the front of the train, then and the train is moving at 100 meters per second, say, then they will observe that this person is moving there at a speed of 110 meters per second toward in the direction that the train is traveling. So let's do an example problem. A passenger on a boat moving at 1.7 meters per second on a still lake walks up a flight of stairs at a speed of 0.6 meters per second. So the stairs are angled at 45 degrees, pointing in the direction of motion as shown. Okay, so let's do this problem. What we're going to do is try to find the velocity of this guy here, the velocity of the man from the reference point of, say, somebody who's sitting on the shore. Okay, so the velocity of the man as seen on the shore, so from shore, it's going to be equal to the velocity of the man on the boat plus the velocity of the boat as seen from the shore. And of course, this is a vector relationship. So the velocity of the man from the reference point of the boat is just 0.6 meters per second at 45 degrees. So 45 degrees, so this is a 45-degree triangle here, right? So if I do some simple trig, right, he's going along at 0.6 meters per second, right? His x component velocity here is going to be 0.6 meters per second times the cosine of 45 degrees, which is 1 over root 2. And his velocity in the y direction is going to be 0.6 meters per second times the sine of 45 degrees, which is also just 1 over root 2. Okay, and 0.6 times 1 over root 2 is 0.42. So this one here is 0.42 meters per second I hat plus 0.42 meters per second j hat direction. And the velocity of the boat from the standpoint of the shore is 1.70 meters per second in the x direction, so in the I hat direction. And that means that the overall velocity is 2.12 meters per second in the I hat direction plus 0.42 meters per second in the j hat direction. Put a box around my answer. I was asked to find a vector quantity, so I have this in I have both magnitude and direction included here, right? I have I have so both magnitude and direction, and I've used units, and I've put a box around my answer so that whoever's grading my work will have an easier time of finding the answer. Let's go on to the next thing. Finally, we're at projectile motion, or sometimes I like to call it projectile motion, just because it sounds kind of fancy. So, projectile motion. As we had said earlier, right, the motion of x and y components are independent. So, for an object that's undergoing uniform acceleration in the y direction, the kinematic equations at constant acceleration, or the KECA, will apply, right, for all the y components, and that will not affect the x components at all. So, here are the kinematic equations at constant acceleration. In the case of projectile motion, when we're neglecting air resistance, then the acceleration in y is going to be minus g, right, which is minus 9.8 meters per second squared, right, in the case that we have the ground here and the y-axis is pointing up, right, towards the sky. Then we have an acceleration pointing down, and the little g is 9.8 meters per second squared. And meanwhile, the acceleration in the x direction is 0. So that means that the velocity in the x direction doesn't change at all. It's going to be the same for all times. And so the equation of motion is really simple, right? X is just vx times t. That's it, no acceleration. So if we have a projectile that's launched at a speed of v0 and it goes up at an angle theta, then its initial velocity vector is going to be, right, v0 cosine theta in its x component and v0 sine theta in its y component. And we can get the following equations when we substitute these in for each one of the kinematic equations at constant acceleration. So we have the velocity is just the initial, the velocity in y is just the initial y velocity minus g times t, and we have y is v0 sine theta t minus 1/2 gt squared, right, where the velocity in y is pointing up. And finally, we have the velocity, the squared velocities, initial and final, related by this equation here. So note that if we know v0 and we know theta, then we can determine the exact location and velocity of the projectile at any given time. Okay, let's do another example problem. So I'm gonna ask that you pause the video for a second here and start trying to do the equation yourself before you look at me solve the problem. First thing to do in this case is to draw a picture, because there was no picture, so that's what I did. And some other good practices to start you out solving physics problems and to get this down is to write down the given quantities, write down the unknown quantities, and then start thinking about, okay, what have I been learning about lately? What are the equations that might be useful for this? And to figure out how then you can get the desired quantities from what you were given in the problem. So if we just quickly read the problem together, right? A tiger leaps horizontally from a 7.5 meter high rock with a speed of 3.2 meters per second. How long is the tiger in the air, and how far from the base of the rock will she land? Okay, what if she leaps at 6.2 meters per second? How do those values compare? So write down what's given and what's asked of you, and then try and solve the problem on your own. Okay. Assuming that you've done that already, I will solve the problem. So I'm given here that change in y is 7.5 meters, and I'm given that Vx0 is 3.2 meters per second. Those are good things to know. So I drew the vectors in on my problem here, right? The velocity vector jumping off and the height that she's jumping off of the cliff. So I can plug these in to my kinematic equations that I know, right? The theta here made this pretty easy. Simplified the problem quite a bit, right? Theta is 0 degrees because horizontal, because it was a horizontal leap. So that makes things really nice. The velocity x initial then is 3.2 meters per second, and velocity y0 is 0. Okay, how long is the tiger in the air, and how far from the base of the rock will she land? Well, if I get the time first, then I'll be able to find the change in x overall. So that will follow as soon as I figure out the time. So let's figure out the time first. So I have the change in y is vy0t plus 1/2 g. I'm going to use a coordinate system here where I have y, the y coordinate is pointing down, positive y goes down. So I'll use vy0t plus 1/2 gt squared, right? The initial velocity in y was 0, so this term goes away, right? That's 0. This is known, that's known, and this is what we're asked for, so this looks great. Let's do some algebra. 7.5 meters equals 1/2 times 9.8 meters per second squared. Plugging this into my calculator, I have that t is equal to 1.24 seconds. Okay, great. Now, I was also asked to find how far from the base of the rock will she land. Well, that's not too bad, right? Change in x is just equal to vx0t, and there would be this plus 1/2 at squared term, but acceleration is 0 in the x direction, so that's not so bad. And I have, this was 3.2 meters per second, right, times 1.24 seconds, and 3.2 times 1.24 is 3.97 meters, or about 4 meters. So the tiger lands 3.97 meters away, and that whole process takes about 1.24 seconds. Now, plugging in this other value here is something I'll let you do on your own. We can go on to the next problem. All right, now, a fire hose held near the ground shoots water at a speed of 6.5 meters per second. At what angle should the nozzle point in order that the water land 2.5 meters away? All right, we're also asked, why are there two different angles? And we're asked to sketch the two trajectories. So, okay, this problem is a bit harder than the other one. So, it would be nice to consult some problem-solving strategies to make sure that I'm doing the optimal procedure as I'm trying to solve this problem. Okay, so it says, here's some good problem-solving techniques. I'll post this to Blackboard, by the way. Read the problem, then read it again. We'll do that. Draw a sketch. We already have one. Make sure to write down the givens and the knowns, the given and the known quantities, and then what you're asked to find. Okay, I already told you that one. We'll make sure to do that. And then we're going to think about which principles link the quantities to be determined to those that are known. Okay, well, we kind of know which principles are going to be used to solve the problem, right? These are the equations for projectile motion. Which of these are going to be useful for us? We'll pick out the ones that are going to be useful in a minute. Okay, and we're going to use those principles to solve the problem. Okay, so first we're going to read the problem again. And I like to go through and underline things that are helpful. Okay, a fire hose held near the ground shoots water at a speed of 6.5 meters per second. Okay, so I'm given V0 is 6.5 meters per second. Okay, at what angle should the nozzle point in order that the water land 2.5 meters away? Why are there two different angles? Sketch the two trajectories. Okay, so it's going to land 2.5 meters away, so delta x is going to be 2.5 meters. All right, what angle? All right, so we're asked to find the angle, theta. Okay, we know the initial speed and we know delta x. We want to find the angle. All right, so something to note here about, so these are all the kinematic equations that'll be helpful for us for projectile motion. Notice, right, this final speed here, there's a final speed here. These equations aren't going to be helpful for us, right? Because we don't need to know the final speed. Nobody's asked us that. So we don't need those. This and this here are going to be the money equations, right? Because we're given delta x for the full path, so that's helpful. And we're given v0 as well, right? So we know these two things. We don't know the time, but that should be okay because we know, right, if we start and end at the same point, then our total delta y is going to be 0, right, over the entire path. So we can count that as a known. And so we have here two equations. We have, I'll circle all the known quantities. Okay, we have two equations here. That's a known, that's a known. These two things here are knowns. Okay, we don't know theta. That's what we're trying to find, right? That's okay, though, because we have two equations, right? One here, two here. Right? We have two equations, and we have two unknowns, right? The theta that we're supposed to find, and then there's a t. So I have my two equations, and I'll just go ahead and plug in some numbers. So this is going to be, right, 2.5. This is going to be 6.5 there and there. All right, so if I take this and I solve this for time, I'll have t is equal to delta x over v0 cosine theta. So that's going to be 2.5 meters divided by 6.5 meters per second times cosine theta. Okay. And how about I take this equation and I stick it in here. But the first thing that I could do just to simplify is take this thing and simplify it, right? So if we consider the entire path, right, going up and down, okay, it's going to start at some value y that's 0, and it's going to end at some value y that's 0. So throughout the whole time, if we take the entire trajectory, right, the change in y is going to be 0. Right? So I can use that v0 then equals v0 sine theta t minus 1/2 gt squared. Okay, so let's then add 1/2 gt squared to both sides of this equation. Right, if we do that, then this here just becomes an equal sign. And I can divide then by t on both sides, get rid of the t's there. All right, I'll have here that t is equal to v0 sine theta over 1/2 g. Okay, in other words, it's equal to 6.5 meters per second sine theta over 1/2 9.8 meters per second squared. Okay, that's really awesome. Now, I can plug all of these things, or I can take these two things and I can set them equal, right? I have a t, I've solved this one for t and I solved that one for t, so why don't I just take and set the two things equal? And if I do that, right, let's plug in some numbers first. So this then is 0.385 seconds over cosine of theta. All right, and this one here is, plugging these numbers into my calculator, t is 1.33 seconds times sine theta. Okay, great. And I can take these two things and set them equal to each other. Right. I have 0.385 seconds over cosine theta equals 1.33 seconds sine theta. Or in other words, if I just multiply by cosine theta on both sides, divide by 1.33 seconds on both sides, I have that sine theta times cosine theta is equal to 0.29. Okay, now that's pretty close to the answer. I'm not quite done because I have to solve for theta, but that's pretty close, and if you got to that point on a test, say, I'd give you most of the points. Let's reconsult back to our problem-solving strategies. Okay, so here it says, part 6, we're supposed to use the principles that apply to the situation to guide you to, the equation that you need, and then solve it, right? And so right from the outset, I counted the number of equations that we had to see if we had the right number of unknowns. So note, we're down to here one equation with one unknown, which means it's basically solved. We just have some more math to do, right? And I've been using symbols, right, not numbers, and then it's nice that cancellation of units provides a check on your answer. So make sure to do that when you're solving these problems at home, right? And then the final thing here, it says, does it make sense? That's a useful question to ask yourself, right, once we get to the end. Okay, so let's just solve these. Solve this for theta. Okay, so this looks pretty tough, but trig identities are, we can find a lot of trig identities by just noting, right, that sine squared plus cosine squared is equal to 1. So this is kind of the one trig identity that you need to remember. Then you can kind of derive everything else that you need from this, right? A helpful thing for our equation, right, would be to get, instead of the sine theta cosine times cosine theta equal to something, is to have this in terms of one quantity, and then we could at least solve for that one. So let's do that by just noting, right, this would imply, right, that sine squared theta is equal to 1 minus cosine squared theta, or in other words, sine theta is root 1 minus cosine squared theta. Let's put that in here. We would have then root 1 minus cosine squared theta times cosine theta is equal to 0.29. Well, this we can solve. This we can solve for cosine theta. That's really nice. I'm sick of writing cosine theta and over again, so I'm just going to write u. Right? We'll just substitute that in there, make my life a little bit easier. Okay, so I'm going to square both sides, right, to get rid of this root here. So if I do that, I'll have 1 minus u squared times u squared is equal to 0.29 squared. Okay. In other words, that's 0.089 or 84. And take this down here. Now you'll note, right, that I have just a quadratic equation here, which is really nice. Once I take and distribute the u squared through, I have u squared minus u to the 4th on the left-hand side, I'll just subtract off the, this equals 0.084. Okay, let's get this in a form where I can solve for u more easily. Well, let's see, this would be u to the fourth minus u squared plus 0.084 equals 0. Okay, so I'll take this equation here and I will use the quadratic formula to get u squared, right? So taking u squared, right, that's just cosine theta squared, that's going to be equal to, right, opposite b plus or minus the square root of b squared, it's 1 minus 4ac 4 all over 2a, right? So what I have then is 0.907 or 0.093. Okay, so that means that my cosine theta is equal to, sorry, my angle here, so I can solve this. So I can take this, take each one of these and take the square root of them and take the inverse cosine of that to get the two possible angles that I could have. So I'm going to have theta equal to inverse cosine of root 0.907 or inverse cosine of root 0.093. Okay, so if you take and plug that into your calculator, you will end up with theta equal to 17.7 degrees or 72.3 degrees. Okay, so if I zoom in my two trajectories here, I have one, right, that goes low at 17.7 degrees and another one that goes high at 72.3 degrees, and it goes to the same location in x. The x location, the starting and final, the difference between the starting and final location was fixed, right? But there's two ways to get there at the same, even starting from the same launch speed. So if I draw in this 45-degree angle in here, you'd actually see that if you take 45 minus the 17.7, that's exactly equal to the larger angle, 72.3 minus 45 degrees. So they're each symmetric about the 45-degree angle. Now, there's an important question: does this make sense? And so that was the last thing on the problem-solving tips, right? Once you get an answer, check with your own, intuition or whatever. Just check and see, does this make any sense to you? This should make sense to you if you think about it. You could do this experiment yourself on your desk, throwing up your pen. The launch angle is symmetric about 45 degrees. Now 45 degrees is special, right? Because that's the optimal angle. That's the largest range, right? This is the largest range angle for a given initial launch speed of a projectile. And you can get to a given location by using a small angle or by using a larger angle that goes symmetrically above 45 degrees and then launching it up at the same speed. It'll stay in the air for a lot longer then, but you can do that in such a way that you end up at the exact same location here in the final position. So this is something that makes perfect sense, that there would be two trajectories, one at a smaller angle and one at a larger angle, in order to end up at the exact same spot. So I hope that makes sense to you. I hope that you found this problem interesting. I like this problem a lot, and I will see you next time.